Good morning, everyone. My name is Cheng-Long, a PhD student from KAUST, Saudi Arabia, and today I will overview our recent work extending machine unlearning to dynamic graph data. We term it as inductive graph unlearning. As you know, machine learning has been deeply embedded in our daily life, from recommendations to autonomous vehicles. Understandably, privacy concerns have arisen. Research shows that machine learning models can memorize our sensitive user information and is exploitable by attackers. In response, the right to be forgotten has gained prominence within the broader privacy laws. The EU's GDPR, California CCPA, and the laws in many governments. These regulations now protect people's right to remove their personal information from the servers. As the final step in data ownership, machine learning aims to bridge the legal technical gap. So naively retraining the models on the updated datasets without the unlearned samples is inefficient for continued deletion requests. So the challenges translating the concept into a practical option include locating a single sample's trace in the complex deep learning model and balancing the model's utility and unlearning alignments and reducing the computation costs and governing the process. So when it comes to the real-world graph applications like social network transportation systems and transcription graphs, they introduce more complexity to machine learning. Because we know in graph setting, the node dependencies in the graph data make it difficult to remove one node's contribution without impacting other nodes' contribution in such a message passing chain model. So a straightforward method is applying the SDAIA framework to graphs. This involves partitioning the graph into multiple disjoint shards and training isolated submodels on each shard, which the prediction can be aggregated across submodels. This graph unlearning solution is very, very transparent, but the only problem is how to get a good enough graph partition so that the graph partition has a minimal side effect on the following downstream tasks, since we know the graph partition can destroy the graph structure information. Existing work proposes balanced partition methods. It's okay for the transductive setting, but not applicable to the dynamic graphs. The dynamic graph needs an inductive graph learning procedure. In transductive graph learning, the attributes and the edges of all nodes are visible during training to the model, except the test node labels. The GAN model can make inference for these nodes. For example, predict their labels in the inductive graph setting. All test nodes and their edges are invisible during training. The GAN model is trained on some known graphs and make inference on some totally new graphs with different size and different shape. For example, the transcription graphs are updated every time, and the fraud detection GAN model should incrementally training on those new graphs and predict for new nodes and new edges in the network. So in our work, we first identified the factors blocking the SDAIA framework in the inductive graph setting and solved it. That means the graph partition have to preserve as much structural information of the original graph as possible, while satisfying some constraints, for example, fairness and balance. This is based on our insights that more structural information leads to a higher GAN model performance, and a balanced partition will make the retraining time for each shard is similar, and resulting expected unlearning time cost is small. When facing only some small batch unlearning requests, and a fair partition can improve the utility, since if several shards are unfair for some classes, their corresponding GAN models may make unfair decisions and fail to train good enough classifiers. So, as we have mentioned, different with the transductive setting, there is no help from test graph during the training in the inductive setting. So in this setting, the fairness is more important than is in transductive setting, which can lead to a more robust learning process, as well as the implementation efficiency is also important because it should be very fast so that it's applicable to dynamic graphs. Yeah. And so motivated by our above findings, we propose this guided inductive graph unlearning framework named GUIDE. a brief guide consists of 3 components: guided graph partitioning with fairness and balance, and efficient subgraph repairing, and similarity-based aggregation. For the first component, to satisfy the challenging requirements of graph partition, we first combine the fairness constraint and balance constraints into a single linear constraint on the graph group membership indicator matrix, so that the constrained graph partition problem can be formulated as a special clustering problem with linear constraints. This is a conjugate programming problem with binary variables. To solve it efficiently, we relax the constraints and propose the method of a faster version and a spectral rotation version. Simply speaking, they are both alternating minimization methods, and to the best of our knowledge, this is also the first study on graph partition under fairness and balance constraints at the same time. If you are interested in the technical part of these algorithms, you can refer to our paper for more details. And well, even though we can got the good enough graph partition, the edges between subgraphs are also lost and destroy the graph structural information. To restore this missing information as much as possible, we propose 3 simple subgraph repair methods as the second component of our framework. Through our methods, those nodes who connected to other shards before partition can rebuild their local structure by repair the domain neighbors motivated by the graph's assumption of homopholia assumption. We can fill the domain nodes features by copying from their connected real node or fill with 0 values simply when the homopholia doesn't exist. Yes, and we can control it by a mix-up strategy. Such simple methods can recover the structure of the JNN's computation graph. Yes, and for each shard, our repairing procedure doesn't involve the feature or label information from other shards, so that can keep each shard updated to independent. Yeah, and then when we aggregated the predictions of all submodels, each shard should have an importance score to control its prediction weight during the aggregation. Well, we have got a fair and balanced graph partition and repaired graph computation graph. An averaged importance score is enough to achieve a good result, but a flexible importance score to each shard would make the aggregation more stable under the dynamic graph setting, because there may be a lot of test graphs vary from size to shape. Yes, and different with the previous work, they learning the importance score of all shards at the same time by JN models validation performance. We calculated the similarity score between each subgraph and the test graph using graph kernel method. This is motivated by existing JN research that they say that the behavior of JN model is strongly related to the structure of the training graph, and for an individual JN model, its generalization to unseen nodes requires aligning newly observed subgraphs to the node embedding on which the algorithm has trained. Yes, and a new graph with more similar structures to the training graph is expected to yield a better performance. That we assign those subgraphs which are more similar to the test graph higher importance score during the inference stage. Yeah. Okay, and to quantitatively evaluate the fairness and balance, we define a fairness score and balance score, and to see if the graph partition is good enough. And the results show that our algorithm are superior to baselines with 3 times balance and fairness score. This is helpful to make the sub-JN model to learn a fair representation or make a fair decision aligning with the statistics of the whole graph before the partition. And besides, our graph partition algorithms, for example, the GPFB-SR could achieve comparable computation performance to baselines, and the GPFB-FAST could achieve 10 times speed up on graph partitioning than baselines. They are efficient enough to be implemented for the inductive setting. And the unlearning efficiency of our framework is also comparable to baselines, especially when the batch size of unlearning requests is small, that the unlearning only involved a few shards. Yeah. And again, as shown in this table, all 3 subgraph repairing strategies are helpful in improving the model's performance. The simplest zero feature, just fill the zero value to the domain neighbor, could achieve a over 60% improvement. It's not surprising that the mirror feature neighbor is not as good as zero feature, because in the message passing framework, and the mirror feature's contribution to its neighbor is 0. Yeah. And the mix-up strategy is a trade-off option that depends on the homophily or some heterogeneous graph data, and can be defined a parameter manually. Yeah. And we implement our framework on a Bitcoin transcription fraud detection task over 200,000 nodes, and the GAN model is trained on the first 30 time steps for detecting those illicit entities and make inference on the last 15 time steps. The colored bar in the figure shows that the label composition of each test graph, the GAN model's performance can vary with time steps that the new transcription graph is generated from new node and new connections. Yeah. And the guide performed very close to scratch for 2 metrics during the first 8 time steps, and there is also a clear performance gap between guide and others. Yeah. And during the last 7 time steps, all methods can provide similar macro F1 scores due to the very limited illicit samples in the test graph, while our framework can still produce higher AOC scores than other methods. And we also evaluated our framework on different GAN models, 6 GAN models, and reported average results on 4 graph data sets in the inductive setting. And most of the time, the node classification accuracy of our framework is higher than baselines. And taking the gap between random method and the scratch as 100%, we can calculate the normalized score of those baselines, and our framework can achieve the best performance for almost all models on 4 data sets, and the normalized score are both more than 2 times higher than the result of baselines. Yeah. And we test our framework using the SOTA unlearning privacy attack against machine unlearning, and the AOC of membership attack on guide is close to random guess, showing that our framework is enough to conduct machine learning with lower unlearning privacy risk. Yeah. And in a word, our framework can be efficiently implemented on the inductive graph setting for unlearning and for learning. Yes, because it has a low graph partition cost, no matter on the computation or the structural information. Yes, and we have open sourced our code on GitHub. Welcome to start. Thank you. That's all.